Hi, in this video, we're going to take a look at composition data focused specifically on geospatial statistics. All right, so we're going to be taking some information from the textbook Geostatistics for compositional data with our Chapter 2, Section 2.1, Compositions. All right, so here's the book that we are getting some information from. Here's the name of the authors. University of Central Florida students can download the textbook for free through the library. Now, here is the web page for the GitHub for the package that accompanies the textbook. And here is one of the author's professional websites. All right, so let's talk about closure. Now, I'm not talking about emotional closure. I'm talking about data closure. All right, so composition data, where our observations the measurements are non-negative and they sum to a constant value. So think of like percentages or fractions so that the row in my data frame adds up either to 100 if I've got percentages, all values are 0 or positive, or maybe all rows sum up to 1. And so typically we're going to have composition data stored in our data frames where our observations are corresponding to rows. And in spatial statistics, each row will correspond to a location. All right, and then columns will correspond to specific fields that we're interested in. All right, most of the time, if we don't have a reason not to, we're going to either sum to 1 or 100. 100 for percentages, very easy. 1 for fractions. Whichever one you choose, it doesn't really matter. You just have to be consistent. Now, there's going to be some problems with composition data that we're going to show in a moment. And we're going to get into some really interesting aspects of spurious correlations. I'm going to show you how spurious correlations can just absolutely go wild and crazy depending on what we choose for our data fields that we'll consider. All right, so in some situations, that constant value is not going to be clear from the situation nor the data. So it may be that I don't know what I should use just because of the nature of what I'm working on. It's not clear. Should I like use, rescale to 100? Should I rescale to 1? Should I leave it as is? Leaving it as is, what should the value be? All right, so when the data does not sum to a constant, we have several choices. First and foremost, we could leave the data as is and proceed and just go with it. Now, initially, that seems like a bad choice, but I'll show you in a moment that might actually be the best course of action to go with. We could also rescale the rows of our data to add up to 1, add up to 100. Now, rescaling the observations, the rows, is called closure or reclosure. So, and frequently, reclosure arises in exploratory geochemistry, where samples are diluted, that is, with a variable amount of water, and things, getting into the sample, and that can actually distort the actual signal. Another even clearer case of like doing this reclosure thing is when we have plant tissue samples, the total sum of what we have typically correlates with the age of the plant. And so species composition counted from traps in ecological studies may also belong to this category. And so, when the actual amount that we have is a variable itself, reclosure, is going to have to be something we consider. And so reclosure can be used anytime that we're only interested, so only it needs to be emphasized, only interested in the relationship between subcompositions of the original parts. And now another option that we can go with is to create a filler column to fill in the shortage. So let's say that I know that everything should add up to 100 or 50 or some number, but some of my rows don't add up to that value. Well, what I could do, I could create a filler column to make up that gap. So filler columns are frequently used in mining exploration data where the individual element concentrations are considered proportional to the absolute mass of the abundance and the abundance of each element. And so what we're going to be doing there is that our filler variable accounts for all other elements, all other matter that's not actually being under consideration. So everything that we're not interested in is kind of just thrown into that filler variable, and we leave it alone. All right, so let's look at the R package called compositions. And so here we're just going to look at some examples going on. The compositions package gives us the tools to really do two primary things. One is to be able to declare, hey, this data set is a composition, so treat it as a composition as you work through, as I work in R. Another set of tools in this package is to transform my data into a composition. So two primary aspects that we can use this in. All right, and here there's the When Darling data set. And so this is from, this is ore composition of a bench at a mine in Windarling, West Australia. So the data set contains geochemical compositions and some extra variables in a grade control study of mine bench in West Darling. All right, we have 1,600 rows, 16 columns, and here we can see the range of values. So we can see here these, describe where we are, what's going on. It gives us information, and these columns are our actual composition. And so this is important to be mindful of. All right, so here's the information we're really trying to get at, and here's the ID variable, coordinates, and so on. All right, here's just the head of the data set, so we can just see what's going on. All right, so something I can do when I have my geostatistical data, I can go ahead and extract the coordinates off of here. So here I'm taking easting and northing, which are the coordinates of what's going on. And also I can extract the composition data. So here, this data frame is only the composition. So this is what I'm like primarily interested in for this analysis. All right, so one thing I'm going to want to do is check to see, do I actually have a composition? All right, well, if I go through and I take the row sums, you'll notice that the row sums go as low as 0.68 and as high as 0.87. So these fractions are not adding up to 1. So I know that there's something going on. So for this data set, what's happening is that there's other elements, other chemicals that are present in the soil that we're not interested in, and those just weren't measured. And so what we're going to do, we're going to create an other category to fill in the gap between the row sum and the value of 1. And so I call this composition residual. That way, I like to have very, very explicit names when I do things. And so here, this is a residual. This is the difference between the original row sum and the 1. Now, another data set that's coming from the package is soil geochemistry data from Australia. And so, there's like all this information about what's going on. And we have all of these columns of information if we want to dig into it. And it's a decent sized data set in terms of number of columns. And here there's a good number of actual measurements that we're interested in. These are the ones that are highlighted right now. That other are the ones that we're actually interested for the composition. And I can print everything. Now you'll notice that when I have the names, I have very precise description of what's going on. I have how it's measured, and also we have a threshold on here. So here, anything below this threshold is not considered reliable. And so, in fact, when it's below this threshold, the data frame actually codes the values as negative. And so, I would need to make a decision in my analysis. Do I treat anything below the threshold as 0? Do I, put it at the threshold, half the threshold? What do I do in my analysis? Do I leave it as is? Definitely, I've got negative values there to signal that's below threshold. So I definitely have to deal with the negative values because it doesn't make sense to get negatives for this particular problem. Anything else I want to say? Let's keep on rolling. All right, so let's go ahead and just select some of the variables, convert over to absolute values, compute row sums, and return the summaries. All right, so what I'm going to do is I'm going to restrict to just a few columns. Yeah, the ones I'm interested in for composition. So column 17 through 75. All right, so that is going to be, so this is 16, so 17 through 75 is through here. So we dropped this one. The rest make perfect sense. I'm going with what the authors went with. For some reason, they dropped 16, and then went through and get rid of the negative signs, take the row sums, and leave it as is. So now we have issues with under threshold. We would need to decide how am I going to handle that. For this particular example of this computation, it was just said, hey, do it as, just run with it. Now you'll notice I've got missing values. Missing values are a big deal in composition data because if I do the rescaling, what going through and say I omit the missing values, I'm going to add up all the values in the row and then divide by the sum. All right. Well, what do you do when you have missing values? Do I throw out the entire row? Do I go through and just omit the missing value from the sum, just treat it as zero and rescale anyway? Well, that can throw things off. So if I'm rescaling in that manner, then I mean, really, the ones that don't have missing values, the ones that have missing values can't really be compared with each other. They're not comparable data. So it's a huge issue on what we're going to do with this. All right, so the column names that we saw indicate the analytical methods used to determine each element and its detection limits. So the last value in the column name is the detection limit. These names indicate the potential presence of values below the detection limits, which are recorded with those negative numbers. For example, arsenic, AS, shows 121 negative numbers, which corresponds to values below the threshold of 0.4. So if we find arsenic as AS, see if I can find it for you. All right, like right here, we have arsenic, and the threshold is 0.4. I can go through and I can detect all the times that we have negative values. All right, and so boom, there's 121 in addition to 11 missing values. We would have to make a choice on how to handle this. So missing values I have to deal with. Also, below thresholds, can I trust it? Should I run with it? Should I treat it as zero? You'll have to make that choice based off of your situation. All right, so now the clo function will do closure for us if we go through. So what we can do is I am subsetting the data I had before. Now I'm applying the closure, and now I can look at the row sums this way. So here I run through the absolute values and the row sums, and you'll notice that here I've got that 157 missing values that I saw before. Now, something we need to think about is what if I want to focus only on a smaller set of data? So let's say that I'm only going to consider these 4 columns. All right. Well, then when I go through and do this, my fractions are going to change because I always rescale by the row sums. And so subsetting the columns gives me proportionally different values because other ones were dropped off. And so now we can see, the change. So now let's go into why this is a problem. Now, We can still do this. This is still reasonable, but there are problems with this, and we need to know what those problems are before we make this call on our data analysis. So composition data can suffer from spurious correlations. In a moment, I'm going to demonstrate this to you in a very powerful manner. So Pearson correlation coefficients between any two components, it's not really an inherent intrinsic property of those two components. It depends on the other aspects of the data. So which ones are included, which ones are excluded, will change the Pearson correlation between two columns of data. When I'm doing the rescaling, if I'm rescaling, then what's included, what's excluded from my composition data in terms of variables will change my Pearson correlation. And this leads to the spurious correlation problem, in that we can, depending on which subset of columns we choose, I'm going to get a different correlation. So it might be by happenstance, I might just happen to choose the columns of data that will give me the biggest correlation for two particular variables. So I think I have a correlation when I don't. It's by happenstance of the variable that I selected. So let's demonstrate this. All right, so when we rescale our composition data, the correlation between two variables depend on the other variables included in the composition. So why is this? The denominators of the closure change with the inclusion, exclusion of other variables. All right, so remember that. What I'm going to do, I'm going to select a subset of my columns of my data for my analysis, for my closure. All right, so I'm going to rescale after I make that choice. Okay, well, I kicked out some columns of data. I kept some in. However I chose to do that, that changes the row sum across the board. When I go and divide by the row sum, now I've got different values than if I would have gone with a different choice of columns to include, exclude. All right, so, and also, in addition to this, we have to consider missing values. Missing values are a big deal for closure data. All right, so if I choose to rescale by omitting the missing values in the sum, that's effectively treating missing values as 0 in the denominator, that's going to give me a different result than if I just omit observations with missing values, which will give me a different value if I impute prior to rescaling. And so whatever I choose to do will have a huge impact on the outcome of my results. All right, so when I rescale by omitting missing values, I'm going to end up having non-comparable data. And so maybe I'll compare the rows anyway, depending on my project. Maybe I won't, but I have to be very, very mindful of the impact that can have on my conclusions. That I might end up mistakenly doing comparing apples to oranges. They're both fruit, but they shouldn't be compared to each other unless I just don't have other options. All right, now what I want to do here, I want to go through and demonstrate spurious correlations to you. Okay, so what I'm going to do, I'm going to go through. I'm going to go with every possible composition subset of columns I could possibly do. All right, so if I have, let's say I have let's say I have 8 columns of data. If I have 8 columns of data, then I'm going to have 2 to the power of 8, 256 possible subsets of the columns to select. Now that includes the full, that includes subsets of one observation or one column, and then that also includes the empty sets. Okay, so I'm talking about correlations. So the empty set doesn't make sense, and with correlations, it doesn't make sense to have just one column by itself. All right, so we're going to reduce down to, I think it was down to 247 total possible subsets. Now, so on each one of these, I'm going to go with every possible composition subset I possibly could, and then I'm going to compute all the correlations with that data after I rescale. And then I'm going to look at all the different correlations. All right, and so this code is just running through and generating all of those, or computing all those correlations. And I'm storing everything in nice lists, and everything's pretty clean. And so MCore is going to be a matrix of the correlation, or it's actually a data frame of all the correlations, where I have, first and second are two different columns in the data. So, and let's go ahead and take a look at this. All right, so the one I'm going to focus on here is going to be aluminum 203 and silicone 02. All right, so here, the largest correlation in the entire data set is between these two, correlation of 0.643. That looks pretty big, that looks statistically significant. And we get this when we use this composition. So here we can see the two columns of interest. Then we have iron, phosphorus, and sulfur, I think. I'm not a chemist, I'm a mathematician. I can't really remember, but I know where to look it up. All right, so now this is the highest one of the entire data set. Now, how does that correlation change if I change the composition? Good question. Let's go ahead and see what happens. All right, well, what if I only considered the composition of those two and didn't consider any other columns of data? You can see that, boom, I have -1 correlation. Holy cow, perfect negative correlation. A moment ago, I was looking at a correlation of 0.64. I was like, wow, that's statistically significant and it's positive. It's a decent amount, decent correlation. Now, first thing in this data set is the as far away as possible -1 correlation. All right, it's going to work out that when I have a composition of exactly two columns, 100% guaranteed, no matter what you do, the correlation is going to be -1 every single time. Okay, and now let's go ahead and just start looking through, and you'll notice that when I have fewer columns included in the composition, we tend to get more extreme negative values. And then as we get more and more, there's like more of an opportunity for there to be positive values for the correlation. And so down here, you can see that we have a pretty solid correlation for all of these compositions, but we also have a very solid negative correlation for these compositions. And so I got different values. Which one's right? I don't know. There's no way for me to truly know what the right one is. And so this is spurious correlations. So whatever the correct value is, more than likely it's less than 0.64. So this 0.64 makes things look, it makes it look more correlated than it really is. What is a correlation? I don't actually know. I've got an idea of a range, but that's a pretty wide range from -1 to 0.64. Now, I chose this combination because it's the most extreme example to drive home the point. But now I'm going to show you every single possible pair I can come up with, what the range of correlations looks like. All right, so now if I take every single possible combination, I've got here, I set it up so that each column appears exactly, each pair appears exactly once in this. Remember, the correlation with A and B is the same as the correlation with B with A. Order doesn't matter for correlation. So this is all possible pairs where orders doesn't matter. Now here, you'll notice on this one, I've got a -1 as the minimum value and a negative 0.93 as the maximum value. All right, so I mean, that's pretty solid evidence that these are negatively correlated with each other in the data set. Like I'm pretty strong, pretty confident that's a negative correlation, and it's pretty substantial. you'll notice that every single minimum correlation for every single possible pair is -1. That's because every time that I have exactly two variables in a composition, I will have a negative correlation of -1 every single time. No matter what you do mathematically, it will work out. Now, just to show you what's going on, I've got the median of all possible correlations, the mean, the average of all possible correlations, and then the maximum. And it's ordered by the maximum value on this. So as I scroll down, we can see here we have quite a wide range of observed correlations. And so if I was, running my analysis and I saw, for these two, I saw a 0.55 correlation. I go, wow, that's positively correlated. There must be something going on. Maybe, maybe not. You don't know. And so when we do compositions, Pearson's correlation is sensitive to what was included, what was excluded in the data, and that's also what was included, what was excluded in the sampling. So if measurements weren't even taken, I have no possibility of ever detecting those aspects. All right, so the constant sum constraint sets it up so that for one value to increase, another must decrease, right? So if all of my entries in a row adds up to 100 and one value increases, well, that means somewhere else, something, at least one has to decrease to maintain that constant value. Also, if one value decreases, then somewhere at least one has to increase to keep it adding up to 100. All right, and so because of this, like, we're just going to be very set up to have a negative correlation when I'm dealing with compositions. And so we have a negative bias on our correlations. Variance covariance matrices will always row sum or column sum to negative values up to machine accuracy. Now, variance is always positive, so that means that we're going to have a positive value plus all of the covariances, which adds up to a negative value guaranteed. So this is setting it up so that we're biased on our covariances being negative no matter what. And some of the covariances are going to be negative even when the data is not comparable. All right, so here just to show you, I'm taking the covariance of the composition of all the values. If I take the row sums or the column sums, I'm going to get exactly the same value. And you'll notice I've got negative, I've got negative, I've got negative, 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 negative. Now these positive values, you'll notice that these are really, really small, right? The positive values are very, very small in the sum of the variance covariances. And we can see that I mean, really, this is within machine accuracy. And if I remove the variance, like if I got rid of the zeros on the diagonal and then did these sums, we would see stronger negative values. All right, so this sets it up that it can hinder our interpretation of our correlation coefficients. So the correlation is no longer linked to zero Pearson correlation. So no correlation doesn't have that strong connection to zero Pearson correlation that we are very, very accustomed to. And we're taught that from the very beginning, from the moment we learn about correlation. This aspect is super important, zero and no correlation. Now, it's even like harder to figure out because we have that negative bias. Also, this sets it up so that our covariance matrices are singular. They're non-invertible. So this jeopardizes the use of many statistical methods, from covariance matrices or principal component analysis to cluster analysis, variograms, and covariance functions, which must sum to zero for any lag. So, I mean, this really throws off like a bunch of things that at first glance, if I didn't understand matrix algebra, I wouldn't even be aware of. All right, so just to show you the singularity aspect, here I've got the eigenvalue. So here's the largest eigenvalue of 007. Here we can see that the second eigenvalue, and they're ordered by magnitude. Here, this is, oh, and also, this is a semi-definite matrix for sure. Therefore, the eigenvalues have to be non-negative. All right, so here, this is order of magnitude less than eigenvalue 1, order of magnitude less. Now here, we start dropping off by quite a bit. And by this point, you can see that's 0 eigenvalue up to machine accuracy. And so we can see that our covariance matrix has to be non-singular, or it has to be a singular matrix. All right, so what we're going to do, we want to use techniques in our analysis that adhere to two possible two properties. First one is subcompositional coherence and scale invariance. All right, and we want these both to be satisfied whenever we do composition analysis. Subcompositional coherence implies that the results obtained in the analysis of subcompositions do not contradict the results of using the whole composition. So if I run a subcomposition analysis and my results contradict when I use all of the columns, then I don't trust that result. So there's something more important. I'm more focused on it. I look at only those columns. I dig in and I see that if I consider the whole set of columns, I get contradictory results. I don't trust the subcomposition analysis in that situation. Spurious correlations show that the Pearson correlation is not subcompositionally coherent. Also, Euclidean distance is not subcompositionally coherent. All right, this is a big deal because Pearson correlation, Euclidean distance, these are like the most basic fundamental tools that we have in analysis, and they're not coherent. So we definitely need to proceed with caution as we start digging in. So now scale invariance proposes that the results should be the same for a composition or a rescaled version for any constant rescaling scalar. And so such as the composition resulting from a change of units from percentage to parts per million. And so I could dig into a mathematical proof and show that this condition implies working with ratios of the original parts. Now, alternative frameworks to compositions. So scale invariance sets relative importance of compositions versus another to a constant value. And so that's something for us to make sure we understand. And in fact, scale invariance implies an equivalence relation on our data where every possible value or every possible row of data I could observe is equivalent to each other if I could rescale my entire data set and get the same value. So the equivalence relation is on all possible rescalings. Closing observations at 1 is just choosing a representative for each class. So I could close on by rescaling to 1, 10, 20, 50, million, 100. Typically we use 1 or 100. Another approach would be to assume that there's an accessory variable playing the role of the total. In this way, one could recover the original non-closed values, which could then be analyzed free of the sum constraint, but not free of that positive constraint. And a good accessory variable for this case is the density. And this idea is particularly relevant in applications in mining and environmental monitoring. Another approach assumes that the composition itself provides information about the total. And so in future videos, we'll dig into these aspects. All right. I hope you found this to be an interesting video, specifically the spurious correlations. If you want, go find some data, rescale things, do some composition, check to see how much your correlations can vary. I didn't think it would vary as much as it did. I think this is really exciting. And well, that's all I've got for you. Life is short. Do math.